Okay, so because the body, okay, doesn't move along the ground, it's projected or thrown in air. In air, we are looking at picturing it horizontally. Air resistance is neglected. Okay, gravity doesn't affect the motion of bodies horizontally. Then friction also doesn't come in because the body is not in contact with the ground. And so all factors that would have to reduce the velocity is non-existent. It means that the body's initial velocity would always be conserved. The initial velocity would be equal to the final velocity because the factors above are non-existent. So the reason why in the horizontal analysis, initial velocity would be equal to the final velocity is that all these factors are not there. So what we start with is what the body ends with horizontally. Are you okay? Are you okay?
Yes, please. Yes,
So
please.
under projectile motion horizontally, initial velocity is equal to final velocity. So we've looked at velocity analysis. Now let's get an expression or equation for determining the horizontal distances covered at different times t, t1, t2. At t1, we realize that horizontally the body will cover a distance x1, okay? At t2, the body will cover a horizontal distance x2. At t3, the body will cover a horizontal distance x3. What is the equation that would allow us to derive this horizontal displacement at any given time t? Please, are you okay? Now, we can use the equations of motion. If we use v squared is equal to u squared plus 2 as, or s is equal to ut plus half at squared. We are looking for an equation for the displacement x1, x2 at any given time t1, t2, t3. If we use equation 3, we realize that because horizontally initial velocity is equal to final velocity, what do you think will be acceleration A? What do you think will be A? The acceleration of the body, A.
0.
It will be 0. Because this is 0, we'll have final velocity being equal to initial velocity, confirming the same equation. Because the initial velocity is equal to final velocity, the body will not accelerate. So this part will be 0, and so we'll have v equal to u. Now let's look at this other equation. S is equal to ut plus half at squared. S. And then with this equation, because a is equal to 0, we only have s is equal to ut. Are we okay?
Yes,
What it means is that if I want the horizontal displacement at any given time, it means that x, and here the s is represented by x1. x1 would be equal to u the velocity of projection times the time taken to come here, T1. If I want x2, the horizontal displacement of the body x2 would have to be equal to u times the time taken for the body to come here, T3, 2. If I want x3, it must be equal to u times T3. If there is x4, S4 will be equal to U times T4, on and on and on. So generally, for one-dimensional projectile motion, whenever you are looking for a horizontal distance covered, either X, it must be equal to U times T. Please, are we okay?
Yes, please.
It must be equal to U times T. Now, you see, let me take you through some key terms. There are some terms that are often applied in projectile motion. This is T1, T2. When the body hits on the ground, the total time taken during the whole journey of the body is what we call as the time of flight. So capital T is used to represent the time of flight. And what's the time of flight? The time of flight is the total time taken during the whole flight or the flight. The flight of the projectile. Then you see this total x1, x2, and then x3. Okay, this is the horizontal distance covered by the body at the time T1. This is horizontal distance covered by the body at the time T2. Then the total horizontal distance covered by the body is what we describe as the range. So x3 can also be termed as the range. And then T3 can also be termed as the time of flight, right? So the range R is the total horizontal distance covered by the projectile. The total.
That's the screen a little to face the board.
Okay, I have. Is it better?
Yes, please. Thank you.
So the time of flight is the total time taken during the flight of the projectile, and then the range, capital R, is the total horizontal distance covered by the projectile. And so the range R is equal to U times T. The range is equal to the velocity of projection times the time of flight. Let me create a question. Then we apply how to use this to solve problems before we look at the vertical analysis.
Mr. Dia,
Hello.
so when you are calculating the time of the flight, will you add all the times together?
Oh no. When we finish the vertical analysis as well, you understand how to calculate for the time of flight. Okay.
Okay.
Let me. Please, are you done? I want to redirect the camera. So a body is given a horizontal initial velocity, 20 meters per second from a height 10 meters from the ground. Okay, from a height 10 meters from the ground. If the time of flight is 4 seconds, calculate I, the range, the horizontal distance after 1.5 seconds. All right, start work. Let's see what you can produce out of this, okay? Finished? Okay, so let's look at it. If we look at the first question, we have the initial velocity of projection u, okay, to be 20 meter per second. Then the vertical height from the ground, h, is equal to 10 meter. Then the time of flight is also equal to 4 seconds. We have to determine the range. I is equal to R is equal to U times the time of flight. So here, once we have U to be 20, the time of flight to be 4, the range would be equal to 80 meters. What it means is that when the body is fired with that initial velocity, horizontally, the body will travel a distance of 80 meters before, yes, it will travel a horizontal distance of this. Please, are we okay? Are we okay? Okay. Then the horizontal distance after a time t is equal to 1.5. So we are looking at x, a horizontal distance x. But we know generally x is equal to u times t. And so u is constant. For u, it is constant during the whole motion. At any given time, the value of the initial velocity there is constant. So 20 meters per second times a time of 1.5. This 20 by 15 on 10. And this will give us 30 meters. So it means after 1.5 seconds, the body will travel as much as 30 meters horizontally. Please, are we okay?
Yes, please.
Yes.
All right. Now, how do you identify whether this is one-dimensional projectile motion or two-dimensional projectile motion? You see, what to help you out in such a situation is that a body is given a horizontal initial velocity. A horizontal initial velocity. Once it is given a horizontal initial velocity, it means if the body is here, the initial velocity given to it is purely horizontal, okay, parallel to the ground, okay. So this adjective describes or indicates that it's a one-dimensional projectile motion. If the body is given a horizontal velocity or initial velocity of so and so, then it suggests that this is one-dimensional projectile motion. Any question? Any question? All right. Then let's look at the vertical analysis of the motion. The vertical analysis of the motion. The vertical analysis of the motion. So vertical. You see, as I said, in projectile motion, we ignore air resistance. So air resistance is neglected.
Mr. Please, can you address us, please?
I will. Okay. I'm coming. So air resistance is always neglected. You can neglect air resistance. Gravity would have no effect horizontally, but for gravity, you can eliminate it vertically because the nature of gravity is such that when a body tries to increase its height from the surface of the ground, then gravity will show you where the power lies. Its pull on you would be great. So you can, vertically, we can eliminate air, effect of air resistance, but we cannot eliminate gravity. So gravity would always be around vertically. But as at the point the body is thrown, the velocity given to the body, let me redraw this part. Let me redraw this. The body is given an initial velocity u. As at the point where the object is thrown, the direction of the velocity given, okay, holding an object and throwing it to somebody, okay, on the ground from a height. You see, when you throw, the direction of the velocity given to the object is purely or 100% horizontal at the point of throw. Okay, so imagine yourself on the second floor of a building, of a story building, and throwing an object to a friend standing down. You see, initially, the object would have to be thrown given an initial velocity here. So the velocity given to the object initially is purely horizontal. So the initial velocity, horizontal velocity, is equal to whatever velocity given. If it is 10, it is 10. Everything, every magnitude of this is equal to the initial. The vertical component is 0 because the throw is purely horizontal initially. Please, are we okay?
Please come again.
So, as I said, imagine yourself throwing an object to a friend, okay, standing on the ground, whilst you find yourself on the first floor, second floor, or whatever floor of a story building. At the initial throw, as you begin to project or throw the body to the person, the initial direction of the velocity given to the body is purely horizontal and 0 vertical. Is that okay? It's purely horizontal. The direction of throw is purely horizontal and no vertical components. So when we look at the point of throw, the initial velocity of the body is equal to whatever speed or velocity given to the body. But initially, the vertical component of that velocity is 0. Okay, so at the point of throw, the initial vertical velocity, V, is equal to 0. Are we fine? At the point of throw, V is equal to 0. However, as time goes by, after T1, T2, then you realize that due to gravity, the vertical velocity will be increasing. So at T1, okay, the body is beginning to be directed vertically and it's coming down. So this part, okay, at T1, there is this vertical component which is coming in. At T2, there is this vertical component coming. At T3, we have a complete vertical component HY. Okay, Phoebe.
So please, I don't understand.
Phoebe, I said, imagine yourself standing on a story building and then throwing a body, an object to a friend standing on the ground. Okay. You begin by, if there's the object, okay, you throw the object in this direction, isn't it? Okay.
Yes, please.
By
Yes,
doing
please.
this, the initial velocity given to the body is completely horizontal. It has no vertical component. That is why we said U is equal to whatever velocity given to it, but V is equal to 0. So U subscript x to denote horizontal is equal to 10 by U Vy. Let me even use Uy instead of Vy. Uy is equal to 0. Phoebe, are you okay?
Yeah.
Hello.
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 Please. Mr. Japan, you are trying to say that from when the ball is thrown, it has been given initial velocity.
Yes.
So like it is left alone. So it will do like it is free falling. Something like that. Right?
Exactly. But at the point, at the just few seconds after throw, every velocity is purely horizontal. Hence, Ux is equal to whatever velocity given to it. If 10 is 10, if 20 is 20. But Uy, it has no vertical velocity because of the initial directional throw of the body. Are you okay?
Okay.
But after
Please.
after time t, you realize that the body's part is beginning to shape or to take a vertical direction. So, okay, after T1, this would have the vertical height y1. After T2, this will have a vertical height y2. After T3, it has y3. But at the very beginning, it has no y component. So the initial vertical velocity is 0, but as time goes by, it will be free falling, just as you said. It will be free falling, and so it will begin to have velocity with respect to time. As time increases, its velocity too will be increasing. So if we want to determine the velocity after a time t1, using equation 1, v is equal to u plus t. Please.
If you touch it, I'll beat you.
Guys, don't beat him. Mute yourself. Rather mute yourself. Don't beat him. Okay, so the particle is here. I want to determine the velocity here. Using this, I can determine the velocity. V would be equal to U is 0. The initial vertical velocity is 0. So if U is 0, V would be equal to G times the time taken to come here, T1. Are we there?
No, please.
Yes.
Using equation 1, we can determine the vertical velocity after any given time. So let's take this to be the velocity here to be V1, the velocity here to be V2. The velocity just before it hits the ground, we are denoting that by V3. So if I want to determine the velocity here, V1, using this equation, initial vertical velocity is equal to 0. So it's like free falling. Therefore, V1 will be equal to V1 times, V1 is equal to G times T1. And T1 is the time taken to move from here to this point. Are we okay?
Yes, please.
Yes.
We can also use V squared is equal to U squared plus 2G S to find the same velocity. V1 squared would be equal to Uy is 0. So 2 times G times, what is S? S is the small vertical height covered, okay? The small vertical height covered with respect to the initial position. And what is that? A vertical height covered by the body with respect to the vertical position. What's that? What's the value? No, we represented that with a letter. What's the letter there? Hello? When the body got here, what is this a vertical height covered with respect to the original position of the body? Hello?
Hi.
Hi.
Okay, so what is the small vertical height covered from with respect to the initial position of the body? What's the initial the letter we use for the vertical height covered by the body? So
Y.
we denoted that by Y1. Okay, so it means that we can find the velocity at this point by taking the square root of 2G Y1. So either the velocity can be calculated in terms of time or in terms of the vertical height. Don't forget 2G, okay, is a constant value. So the only varying situation can be Y. So either you determine the velocity with the time taken for the body to come here, or you determine the velocity with that vertical height covered. Are we okay?
Say.
All right. Then if the body is here,
Yeah.
hello?
It said, yeah. But I thought you said the first velocity will be equal to 0.
I said the initial vertical velocity, the initial at the point of throw, the initial vertical velocity Uy will be equal to 0. But as time goes by, its velocity will be increasing. So it will behave like a free falling body.
Okay, thank you.
So if the body is here and we want to find the velocity there, V2, in terms of time, it will be G times T2. Okay. In terms of vertical height, it will be square root of 2g times y2. So either this one, either this one or this one would give you the velocity at that time. And those values must be equal. If you use time, what it gives you must be the same as if you use the vertical height. Are we okay?
Yes, please.
Now, just before the body hits the ground, what will be the velocity? Just before the body drops. And I'm using just before the body drops because when the body hits the ground, the velocity is 0 because the motion has come to a stop. So I want you to help me get an expression for the velocity of the body just before it drops or it hits the ground in terms of time and in terms of vertical height. Just before the body drops. What will be the velocity there? Yes. In terms of time. Equia. What will be the velocity of the body just before it hits the ground? But I want the velocity in terms of time. What will that be? What will that be? Assuming the velocity is v3. Yes. Equia, are you there?
Yes.
I'm listening. Okay, if anybody is ready, just before the body hits the ground, what will be the velocity?
Mr. Eja,
Hello. Your line is breaking. Reposition. Your line is breaking. No.